Afternoon, everybody who's joined. I think we'll get started. Thanks everybody for joining in as we get started with these talks for the new year. Nik Sultana from IIT was gracious enough to give us a little bit of his time today, and he is going to be talking a little bit about work that he's been doing profiling the network of a federated testbed. So I will hand it over to you, Nik.
Thank you, Jason. Hello, everybody. I'm very happy to be here talking to this crowd about a very kind of technically heavy, data-rich project that we've been working on. And a lot of the credit goes to the other people you see on the title slide here, forming the primary team who worked on this. But as you'll see, as I'll mention along the way, we've also been helped by a lot of other people in lining everything up to make this work and to gather data and to form the kind of insights that this project is yielding. All right, so my plan for today is I'd like to start by telling you why we're doing what we're doing and why do this profiling and why target federated test beds, why Fabric in particular, and what's the value of doing this, be it research or practical. Then I'll also give more background into what makes Fabric special, Fabric's network special, and what makes it maybe more challenging than other types of networks, but also can yield insights that, because of its particular nature, we cannot glean from analyzing other types of networks. Secondarily, then, how does this design, the machinery that we put in place to monitor such a federated network, and how to customize this design to better match the particular features of this network to get what we want to get out of this, and also not put too much load on this on Fabric in this case, and also not make the lives of the operators of Fabric difficult, right? Because we want to make this as unintrusive as possible. And indeed, we succeed in that. I'll tell you about how the system runs and how it runs in user space, so to speak, right? In terms of Fabric's kind of stack. So I'll tell you then a bit about the design and implementation of the system and what we've learned so much by running it. And along the way, I'll also talk about kind of system release and how we're designing this to be used not only by us, but also by others. So feel free to ask questions along the way, or you can keep them at the end if you prefer. I don't mind being interrupted to be asked questions if you have anything urgent that you want to clarify. If you drop questions into the chat, I might not be able to see them. So don't feel bad if you prefer to kind of unmute and ask questions, if that's all right by the organizers, that is. So another thing I wanted to mention is that this is fairly mature work. It's been going on for over a year, but also it's still ongoing work, right? It's work in progress. So any feedback that you wish to offer, we'd be very grateful for. You can do this in the course of this talk, but also feel free to reach out afterwards, whatever works best for you. All right, so let's start from the basics then. What's a network profile? What is it that we want to build? So informally, it gives us a glimpse of what's happening on the network. It characterizes the activity on the network. A little bit more formally, the profile talks about how the traffic and what kind of traffic is traversing the network over time. And then secondarily, we are interested in how this correlates with eyeballs and layer rates and the users of the network, right? And how their intentions are being relayed by the network. But primarily here, the pinhole that we're looking through is that of the data thing, right? So we're focusing very much on the network. Now, in terms of what kind of characteristics that we'd be interested in, and the details that we'll cover in the profile later on, include things like header types and encapsulation patterns and what protocols we end up seeing, encapsulating which other protocols. Obviously, we'd be interested in flows, right? So this is very familiar from any other type of network, right? There's nothing particular here to federated test beds or Fabric in particular. So the concept of network profile is one that's prevalent, right? Whenever you have a network, as we all know, what you don't measure, you can't manage. And so for the good management of networks, we need to have some form of profile being developed. And so one of the things that drives us to kind of do this work on Fabric is because Fabric as a state-of-the-art federated testbed, it plays a very important role in research, in enabling the research of others, right? And we've seen this from predecessors of Fabric, right? They're platforms on which other people carry out research. So it becomes kind of interesting as an object of study in itself. How is Fabric working, and what are people using it for? And this can start to give us insights, informed insights into what are there any clues about its level of maybe utilization or use or trends that can indicate maybe further developments down the line, right? So be it to develop maybe new research into different types of protocols that can facilitate what people are trying to do. So that's kind of one of the key motivations of this work. Another motivation of this work is that from having looked at the work of several other users of Fabric, I can see a certain pattern emerging, right? That to some extent, whenever somebody runs a largest experiment on Fabric, they also set up infrastructure to monitor that experiment, and then kind of the scripts to gather, the results of that monitoring and visualize it. So there is a little bit of a rhyme in all of this, right? There is a little bit of duplicated effort, especially when it comes to monitoring at very high link capacity. And it starts to become a very specialized kind of activity. So it seems that there is a need for a reusable monitoring facility here that other users can use rather than everybody having to largely roll their own. It's a little bit about like how network stacks, right, kind of eventually migrated into the kernel and became general purpose and usable by all the applications that are running on that host, rather than every application having its own network stack. Obviously, there is going to be specialized applications, or maybe applications that are constrained in ways or specialized in ways that maybe have them required to use their own network stack. But for the vast majority of the cases, we want that to be a solved problem. So part of the motivation here is to provide this as a service to others, right? A facility for people to observe their experiments when they're being run on Fabric, and offer them a pipeline to analyze and digest and visualize the results of the network traversals of their experiments in a way that is repeatable and reproducible, without them having to invest research time into doing redevelopment of systems that have already been done. Now, along the way, we encounter various challenges, right? And this is partly why I think it's having such a reusable infrastructure is helpful, to avoid having kind of this wheel having to be reformed every other project or so. So one thing, as I mentioned already, is working at high capacities. Another is the working within the confines of what the testbed provides in terms of what you're able to observe, right? The contract is that we don't expect the testbed to change to accommodate the need for our observability, but rather we want to work with the facilities that the testbed already provides. And finally, flexibility, right? So the need for something that is parameterizable and offers a variable level of detail to the different users who might want to use this facility. All right, so one question that we often get is, well, why not use existing systems? Why not use kind of telemetry from Fabric's infrastructure and use systems like NetFlow and so forth. So there are various good reasons why that doesn't work in this case. So for one thing, typically the users of the testbed don't get access to that information, so that the operator would have to provide access to that information. But even if the operator were to provide access, that information is typically in aggregate, right? So individual users would not be able to typically disentangle their own contribution to the data plane from that of other users. And so then there would have to be some degree of customization, right, and some demultiplexing. And we've tried doing this, right? So we set up a couple of different kind of but mainstream tools, right? Widely used tools. And the kind of out of the box, the information is quite coarse. So the user would still need to invest effort into doing the customization. So the takeaway from here is kind of what I call a bit of a can of pain worms, right? That it's a bit of a can of worms, right? It's something that will yield difficult technical choices, but you still don't overcome the pain that you'd like to avoid for both the operator of the network and the users of the network, right? Because of the degree of customization that will be incurred. All right, so this kind of pushed us towards the direction of something a bit more primitive, while still utilizing the facilities that FABRIC offers for network monitoring, and also kind of at the same time, since I come from a university, right? We try to espouse generality as much as possible. We didn't want to craft something that was too tightly coupled to FABRIC, right? Or tightly coupled to begin with, but rather use very general facilities in order to provide a general monitoring system that can work across federated systems. So in terms of ideas, there are many fellow travelers, right? The idea of network profiling is not new. It's been done for various types of networks, right? So both for, actually for a range of types, right? So domestic internet access and enterprise networks, right? Data centers. Research testbeds are different. They're a different type of network, right? So the insights that we glean from the profiles of other networks don't necessarily transfer over. Some of the techniques do, however, and some of the analysis do transfer over. So that's something that we can build on. Something different here, I would argue, is also the level of transparency, since we're dealing with research infrastructure where the threshold for transparency is arguably higher than what you would expect on commercial systems, right? Where network operators might be, much more conservative, much more reluctant to accidentally leak any, competitive details, right? So I think that there's something here that allows us to do more than what you can achieve in other types of networks in terms of compiling an informative profile. So what are the goals of the project then? So one thing is, so the key goal is to provide a network profiler for FABRIC that is general, that is high performance, that is usable by other people, by other users. And the kind of the two usage modes are for individual FABRIC researchers to profile their experiments, to build a network profile of their experiments. But we're also intrigued by being able to do a testbed-wide profile, right? So periodically getting a read of what's crossing the testbed, right? And what are the trends there. And something interesting to consider is how to do this periodically, right? Or offer it as a service. So we've been running this for over a year now. And in the talk, I'll give you some of the insights that we gleaned. So just in case there are folk on the call who maybe aren't familiar with FABRIC, I'll start with a general description. So FABRIC is a state-of-the-art federated testbed. Federated means that every site is fairly autonomous. Testbed means that it provides resources that researchers can use to carry out experiments. And it works, as you can see, on a continental, indeed intercontinental scale, right? So primarily, it's the density of activity, the center of gravity is in the US, but there's also nodes in Europe, nodes in Asia, and it's not a toy, right? It has very high capacity. It has a lot of resources, far exceeding what any single university testbed can provide. So there is a strength and unity kind of thing going on here, right? So it provides a wealth of resources to carry out experiments. And it is, there are, I think, a couple thousand users, hundreds of projects, many thousands of slices have been created so far. A slice is an abstraction for the resources that you get, right? So it's a subset of, it's a slice of the resources on Fabric that then researchers can do to carry out their experiments. And their experiments typically involve some balance between computation and communication between those slices. And for communication, Fabric offers various types of NICs, including FPGA NICs, which we use in this project for scaling up. It also now offers in deployment programmable switches and high capacity links, right? As you can see in this diagram by Tom Lehman. Now, let me tell you a bit more about how a Fabric site is structured. So I told you that Fabric is a federation of sites, right? And those sites are fairly autonomous. Within a site, typically you have a single rack, and that rack consists of a top of rack, which is then connected to the outer world, including other Fabric sites. So those are the uplinks. And then it also interconnects a variety of nodes consisting of some handful of worker nodes and the head node. And our focus is on monitoring the traffic that is exchanged both within Fabric sites, but also within Fabric sites, right? Within the worker nodes. So when people use Fabric, what they do is they allocate resources. They create VMs on these worker nodes, and they either share or get dedicated access to these NICs here, and they then for the duration of the lifetime of that slice, they get to carry out that experiment. And something else to note is that the slice is exclusive, but it is working over shared infrastructure. So one of the things that kind of motivated us at the start of this, and also kind of persisting during this project, is understanding to a very high level of detail what are the resources that Fabric provides, right? What is this infrastructure? Because this shapes what we can do to monitor it, right? And in fact, it also maybe gives us a better understanding of the constraints within which we are operating. Let me give you some examples of the questions that we typically want answered, right? So, okay, so within Fabric, the key primitive that we're relying on is port mirroring. So going back one slide, the thing that we're going to exploit for our network monitoring is the ability to pick any port in the top of rack, mirror it to another port that is then directly connected to a NIC that we exclusively control, and then hoover in frames from that NIC that have been diverted, mirrored from that original port. That's the only primitive that we're connected in with on the data plane level. Okay, so well, which ports do we mirror? Because there are many more switch ports than there are NICs that we can control. And also there's you realize that immediately there is a tension here, that Patchwork is, the system is using resources on Fabric that are also being used by the researchers, right? So we want to balance the footprint of Fabric, of Patchwork, to avoid being too profligate, right? To be too wasteful. So anyway, maybe we can just monitor the uplinks, or mostly a mix, or maybe a mix of uplinks and worker nodes. We don't really know which direction to go without data, right? So that's something that I'll detail in the next slide. Also, when should we do the sample, right? So are there phases in which the testbed is busier than other phases, in which case the testbed-wide monitor would be more informative than at other times? And how long should we sample for, right? We're using resources on the testbed to do the monitoring. We don't want to overstay, right? Which sites should we sample for, right? So this is also related to when and how long. As I mentioned, Fabric is a federation of sites, right? And they're usually not all busy at the same time. But what does that picture look like, right? Where's the data, right? So that has not, there's no data on this. One of the side effects of this project was to create this kind of meta profile, right? So outside the data plane, we also have a profile of Fabric infrastructure and resources. And finally, directly influencing the design of our system, what data rates should we support? Because if we want to create a profile, we want to capture as much data as possible, and if we want this to be calibrated according to the standard expectations, right? The norms on the testbed in terms of how our users are using it. All right. So first of all, so starting with this kind of meta-analysis, so what is the distribution of uplinks and downlinks across Fabric sites? And as we see, there's many more downlinks, so kind of many more connections within the rack than outside the rack, but also they vary, right? And that's because some sites are more tightly connected than others. All right, so kind of we could monitor a mix of these, but how do we, do we even know if slices typically use multiple sites, or are they typically kind of run on a single site? And this is crucial because this tips the balance between uplink and downlink sites, right? Since there are far fewer uplink ports, it would be great if we can focus on those few and be done. So what does the data tell us? So here I'd like to call out to Nishant Shyam-Kumar and Sean Cummings, right, who were instrumental in gathering some of this data. And what we see is that 66% and change of all Fabric slices use a single site, right? So this is logarithmic. So we uplinks alone don't tell the full story. So the monitor needs to go for a mix of both. And here, a huge thanks also to Kamal and Song from Rensi and from UKY, respectively, who provided some of this data. Okay, so then how long does a slice last for, right? So we know that slices, mostly, the majority of slices are within a single site. And it turns out that most slices, they last for 24 hours. So 75% of slices last for 24 hours. So this answers that earlier question I mentioned, how long should we sample for? So something in the region of 12 to 24 hours would give us, substantial overlap with a lot of slices. And on that subject, how many slices are typically running on Fabric at any one time? So basically the average is 85. And I checked Fabric earlier, its portal, and it was 70 something, right? So we're close to that, right? So the average is 85, and then we have this kind of the standard deviation of about 52. Right. So this gives us kind of an expectation of the level of activity on Fabric as far as allocations are concerned, but it doesn't tell us the full picture in terms of the network, because you could have experiments on Fabric that are mostly burning cores, but not really, burning the transceivers, so to speak, right? So we don't know what the level of activity is on the network yet. So this data, so it's a huge kudos to Bjorn Fexted and Nishant Shyam-Kumar, and also a lot of assistance along the way with Charles Carpenter, who had helped with releasing MFlib and updating it over the last summer to specifically allow the type of data that we're needing to gather for this graph. So let me break it down for you. So what is this showing? So each of these alternate colors is a Fabric switch on a different side. And within this color, each line is a port. So what this is telling us is what is the level of activity of different ports on different sites over time. And we have this data is extremely rich, right? So this, I'm only showing 24 hours here because, I haven't yet found a better way of conveying this succinctly. If anybody has any feedback, and any tips, do get in touch. But basically what this is showing us is on the network side, right, on the data plane side, we have certain ports that are steadily busy, right? Persistently busy. You can see these darker colors, right? So this is a heat map where the darker colors mean essentially higher port activity. And then there are other ports which are sporadic, right? So we see some activity here, then it goes light, and then later on it goes dark again, right? So it gets busy. And then there are occasional events. So these are often experiments, but there might be also maybe management kind of fabric tests that are synchronously running across different ports across different sites, right? So a variety of ports go dark simultaneously. And in my group, we do run experiments that use a bunch of sites simultaneously, right? So I think we're seeing a little bit of that, right? We're seeing that data is crossing the fabric network, and that is showing up in the port stats that we're pulling here. What about the utilization of ports? Okay, so far we started to get an idea that some ports are mostly busy, other ports are less busy, right? But what does the global picture look like? So what this graph is showing is that, well, it's a mix. So if all the ports were fully utilized all of the time, then the graph would be kind of a black line that overlaps with this dashed red line over here. Now, what this means is that about 90% of the let's see, about 90% of the ports are up to 90% utilized, right? So this also means simultaneously is that there's about 18% of the ports that are not utilized, right? So this I see that as they're ports that we have data, but they're not yet connected to anything. So that's how to read this port, right? This graph. So basically, it's saying that 50% of the ports have a peak utilization of at most 38%. And this is also interesting from a Fabric user's point of view, right? Because it gives us an idea of how typically loaded is the network as seen from ports on the switches. And does this mean that it is underutilized? And I don't think it is, right? For various reasons. I mean, one reason is that you always need headroom. You particularly need headroom in a research network because otherwise you will age out of that network sooner, right? Since with research, you typically want to push the envelope in the type of workloads that you want to run. And the third reason is that this is a shared network, right? So you want certainly more headroom because you want to accommodate the potential the simultaneous workloads that different users who don't communicate or synchronize with each other might be running simultaneously. So I think this also kind of it creates interesting questions about how to enable, and improve scheduling and synchronization. But that's a bigger question, right? So, but anyway, so for our purposes, this is telling us that, well, there are ports that are fully utilized, so line rate is the way to go for monitoring. Then I was also interested in how does this load change over time, right? So where are these peaks of the port utilization? And it's interesting this graph kind of you can see certain peaks around April and October. And if we look at the next graph, I'll show you the kind of the aggregate, not just the peaks, but just the volume of traffic over time. So these gray bands here mean that we don't have data, right? So this is data that we have running from the last week of February until, in this case, for this data set, until the last week of November, right? For other data sets, we go throughout the year. In fact, we start from 2023. But this is telling us a bit more about when we should choose to sample, right? We essentially, to form a representative profile of the network, time does matter, right? Because you might happen to be sampling in a quiescent time of the network. So I think a hypothesis is that now turning to the network activity, right? I think it's reasonable to hypothesize that the network activity is correlated with events like SC in November, right? So you can see this ramp up leading all the way up to SC, right, and peaking there, and probably other deadlines as well in the first or early part of the second quarter of the year. But it would be interesting to run this kind of over longer terms to see the persistence in the time series, right? But I think it's reasonable to assume that, or to conclude that the network is going to see a lot more utilization in the ramp up to big events that involve showcasing work based on the network. All right, so we have some answers, right? And these answers, they are part of the meta-analysis related to the work we're doing, but also help shape the technical design of the work we're doing. Because essentially, we need to be able to cater to have a mix for uplink and downlink. So the system we design, needs to be able to make sure or help us or guide us to incorporate both. When we should sample, we can recognize network intensive periods from a ramp up, and maybe there's also a seasonality to this, right? So that we can exploit from year to year. The duration, I think, correlates with the typical workloads duration at the location on Fabric, right? So 12 to 24 hours. And which sites we should sample, right? So using MFlib, right? Using that's the data source of that of the graph, one of the graphs I showed you earlier, right? We can find which are the busiest sites. And data rates, 100 gigabits is a reasonable expectation to set, given what we saw from the data. All right. So one of the things that, as I mentioned earlier, one of the things that we set out to do was to design a system that could monitor Fabric, use resources that Fabric already provides, and not expect any changes on the Fabric side in order to accommodate the system. And indeed, there's been no changes on Fabric sides to accommodate the system, because this system, it runs as an experiment, like any other experiment on Fabric. There's nothing special about this system. What the system does is it uses facilities that Fabric already provides to any other potentially Fabric user, but then develops the logistics, and based on the research I kind of talked through in the previous slides, creates the design that allows for a predictable, high-performance way of obtaining readings and from the data plane, as well as from partly from the control plane, in order to create a profile that is experiment specific or testbed-wide. So Patchwork simply runs as an experiment on Fabric using resources that Fabric already provides, right? The NICs and cores and memory and so forth. So let me walk you through the design of Fabric of Patchwork, right? So there are 4 phases it goes through. So the first phase, setup phase, we acquire resources like any other experiment would, right? And we treat every site autonomously. So when we started Patchwork, we used to kind of group sites into not quite continents, but into batches and into 3 batches. But there we found the design to be brittle, because then if we could not acquire the sufficient number of resources on one side, then the whole batch would fail, right? So okay, fine. We treat sites as being independent. We run as many Patchwork instances as there are sites. And we configure this, and we use parameters that I'll mention in the next step. But we allow some of these parameters to vary. And in particular, we allow which ports we're mirroring to vary, so that we can not necessarily commit to mirroring specific ports, but we can adapt to how low the different ports are becoming over time. So then the observation phase, this is what lasts 12 to 24 hours. So this is where we're hoovering data up. And the parameters that we use are, we truncate it to 100 bytes and we run samples that are 20 seconds long over a port, and we do this every 5 minutes. And what we do is we also kind of adapt the we call this strobing. I'll say more about this in the next slide. Which ports we're monitoring, right? So when we started out, we only used to monitor uplinks, but as I mentioned, based on the data available, that's insufficient, since most Fabric slices are resident on a single slice. So then we collect the capture, right? So this is a fairly straightforward, download step, and then starts kind of a fairly long pipeline of digesting and analyzing this. So we have a very general parallelized framework to do this. It takes, I mentioned that the observation takes, 12 to 24 hours. This phase takes, a multiple of that, several days. So in order to do the analysis, what we do is we use an existing dissector. So we use, Wiresharks/T-Sharks dissector, right, to tell us what those headers are. Getting into the business of writing a dissector, it does not seem like a good use of research time, right? Given that there are state-of-the-art tools out there that can do this for us. And that is where the bulk of the processing time goes. But we get very good data out of that, right? And we rely on the dissection results for subsequent analysis. And then we structure the results in an abstracted format that feeds the later phases of the process. And I'll show you some of the results that emerge from that. All right. So what are some of the really cool features here that we developed over time, right? So these are things that we realized that we needed. And these are exactly the kind of things that anybody who would be doing kind of network profiling at scale on a federated system would need to do in order to do it well. So one thing is loss detection. I told you that we're using we're using port mirroring. So with a port, typically you have two channels, right? You have the transmit and the receive channels. They're unidirectional. When you mirror, you can mirror both, and that way you'll see both sides of the conversation, so to speak. But you then, if the port is 100 gigabits, you would be mirroring 100 gigabits in each direction, and you'd be then trying to siphon that into 100 gigabits port on the next side, right? So you're going to be losing packets. Initially, we were blind to this, right? We knew about this possibility that if that port was being driven at 100 gigabits bidirectionally, we'd be missing traffic, but we didn't know when this was happening, right? So this is something that we fixed using FABRIC's MFlib facility that I mentioned earlier, where we simultaneously poll MFlib to find out, where we exceed our ability to hoover traffic. And there's nothing really we can do about that loss, right? Because that's being lost at the switch. But at least it's good to know that this traffic we're not capturing. Another thing is strobing ports to get more coverage, right? So the selection of ports that we mirror is not fixed. Rather, Nishank devised an ingenious algorithm that picks ports according to their level of activity, but also is biased against starvation, right? So even ports that aren't maybe as active as other ports, we're still interested in sampling them eventually, because maybe the type of traffic that they are relaying is different from the busier, chattier ports. Another feature is offloading to the Alveos, right, which are the FPGA NICs on FABRIC. This is crucial in order to be able to drive this at line rate. So Patchwork can run at two modes. So there's the TCP dump mode, which is part of the tuned infrastructure that we have, and we measured that this can work up to 8.5 gigs. But that's far cry from line rates, by modern standards, certainly. So instead, what we do is we offload this to the FPGA to do filtering, truncation, and any editing of the packets, such as anonymization of addresses and so forth. And then there would be a custom DPDK application running on the host that will receive the truncated traffic from the Alveo and then serialize it, but also have to do some load balancing, because while with DPDK we successfully bypass the kernel in one direction for the kernel, in order to write the file, currently we still have to go to the kernel. So that reveals another bottleneck. I'll say a bit more about that later. And finally, reusability, right? That there's a lot of work that went into documenting this. We went to six alpha releases internally, and got people to test it internally, so that this is usable and reusable, but not only by our group, but really by other people as well in the community. So how well does it work? So here is some kind of data about Patchwork working on FABRIC over time. So this starts in late August until late December. Blue is good in this case. And it mostly works good. Where you're seeing these dips of orange, where orange are failures. Essentially, these were phases of changes that we're making to Patchwork, but also changes that were happening in Fabric simultaneously that did not agree with one another. Right? So we're working through this in order to mostly keep kind of a stable setup. And you might be wondering, well, what do failures look like? Well, failures mean that maybe there is a site that did not have the resources that we needed in order to do the monitoring, right? So there might not be sufficient kind of we use Mellanox cards for the non-FPGA work, right? So maybe there weren't any sufficient Mellanox cards. Several instances where there weren't sufficient cores. Several instances where also the secondary storage was all spoken for on some sites, right? So in which case we wouldn't be able to get any storage allocation to write to during the capturing, right? That we then download from. So that's what failures are, right? They're largely kind of resource mismatches. And that's a site-specific thing, right? So you can still, you might not get everything you want by having a field from all sites, but you can still get most of what you want. So let me tell you a bit about more some outputs from Patchwork. In particular, I'll tell you about the network profile that we've gathered so far. So there are so many ways to slice and dice this. This is kind of a project in itself. It's absolutely fascinating. If anybody has an interest in this, do get in touch. We're swimming in data, and as you'll see from the graphs, we're having a lot of fun looking for ways to convey this data. But basically, this slide captures kind of the first order information that we're looking for here. So first of all, granularity divided in terms of space. So either for the global aggregate testbed or for individual sites on the testbed. And also by time, right? By some interval of time, right? Be it day of the week or hour or month, right? So in this talk, I'll focus on hour of the day. And we're looking for the typical things that you'd look for in a profile, right? So which headers show up, which is indicative of which protocols are being used. What is that? How many headers, different types of headers show up, right? Which gives an indication of what is the testbed being used for. Frame sizes, which also gives an indication of workloads, right? How many flows gives an indication of load and how many bytes there are, and they show the size of the flows. The distribution of frame sizes and sample flows, right? So as we know in protocols like TCP, for example, this varies according to the segment size, right? So whereas other protocols are much more rigid in their datagram sizing, and also encapsulation depth. Okay, so we had given the first kind of version of this. We presented in May based on data we captured in December 2023. So this was a graph that shows for different sites and different ports, what was the distribution of frame sizes. So when we ran this again recently, we were swimming in data, right? So if anybody, sees any opportunity for applying any, artificial ignorance to this, I'm completely with you. There is a lot of interesting analysis that can be done here. But for the sake of being, tractable, we decided we're going to break it down by site. So every port that we're monitoring, we kind of segregated by site. And what we're looking at here are what are the frame sizes that typically show up on different sites over the course of this past year, right? And what we start to see is, okay, there's a variety of sizes, but it does look like it's dominated by this smaller so these are packets or frames rather that are up to 127-ish bytes, but also by the jumbos here at the end. And there's another way we can present this by looking at flow composition. So this is saying, we were to aggregate all the flows in the sites and kind of then make kind of a breakdown by frame sizes inside those flows. What would that kind of CDF look like? And kind of this is telling the same story, but from a different angle, right? So if we take S11, for example, here, we're saying that the composition of flows is mostly small, right? Until then it becomes bigger at the end, right? So if we go back to this graph, we see it's mostly small, and then it becomes bigger there, right? But for the large, so this you can't quite make out. There's a dotted red line here. This is 64 bytes over here, or something close. This is a log plot. So it's mostly small and then becomes bigger. And so yeah, so you kind of this is consistent. We're using the same abstracted site names between the two graphs. Now, we also have flow level analysis, which we presented earlier. I tried doing this for this version, but we simply have so much data that the behavior, the composition of individual flows becomes very difficult to appreciate. So kind of I'm trying to work on kind of clustering to find out what's the typical flow size here. But if anybody has any ideas, happy to discuss that further. Happy to learn. So what's the summary here? So across all of Fabric, the most prevalent frame size is the one that we talked about earlier, up to 127 bytes, that's 63.2%, and then jumbos have a very substantial presence. And this is very different from other types of networks, right? So when I showed this to somebody who typically monitors, Internet Core, they said, "Where are the 1500 byte frames?" Right? Well, on this network, I can understand having jumbo frames because I think some of what we're looking at is DTN-like behavior, right? So you don't want to be segmenting in a very finer grained way than you need, right? Because you'd be paying overhead. All right, now turning to what's on the network, what protocols are on the network, and so our proxy reading for this are headers. What headers are we able to see in the dissection? And your eyes are not deceiving you that over 100%, there's an over 100% occurrence of Ethernet. And so that's the most prevalent header, followed by VLAN at 100%, and then IPv4 and TCP, and then some of TCP is SSH. And so what does this mean? Well, this means that actually there is a lot of encapsulation that's going on, right? So here are some examples where we have Ethernet that's showing up at the most external layer. And then we have a VLAN header, two MPLS headers, pseudo word, since MPLS doesn't have a kind of a next protocol field. And then we have Ethernet again. And this is the world as seen by the network user, right? So the Fabric user. This makes sense to the Fabric user, but this other part makes sense to the infrastructure. And here are two examples of how this shows up, right? So that's why Ethernet is showing up at over 100%, in over 100% of the cases. There's something else we can see across Fabric sites, and here I'm not showing kind of any pseudonyms for Fabric sites because it doesn't really matter, is how many different types of headers do we observe, right? So there's Ethernet and VLAN from the previous examples, but then the dissector also kind of gives a bunch of other types of protocols that are showing up via their headers. So we see this extreme range here, right? So there are some sites where we see fairly low diversity, 18 headers across all the traffic we have, whereas other sites, over 160 types of headers, always, according to the dissector, which is our gospel here, and as I'll mention later, I do suspect that the dissector has false positives, right? So T-chart and Wireshark, I think they see based on some port numbers, they make inferences that are unsubstantiated, not unsubstantiated, but that lack substance. So then what's this blue line here? So blue line is encapsulation depth. So here we're saying, okay, in addition to looking at the variety of headers here, how deeply are they typically stacked, right? And what we find is that they don't go as deep as in a correlated way to the variety of headers, which is what we'd expect, right? But there is quite some variety between that. All right, so I see we're at 10:02, so I'm going to start wrapping up. I'll just talk about a couple of other bits of data that we typically get here, which is kind of the flow-related data, which is, for example, so we run these 20-second samples, and inside these samples we have a reading of what's happening over on the network at that point. And this is an example of a particular site where we have, a lot of the time there aren't, this is about, 10 to 100, actually, this is linear scale here, so about 10 to 100 flows, but sometimes it gets very busy. So another way we're looking at this to kind of represent it in a more global way is by using a box plot. So basically the orange line here is the median, right? And then we kind of this series is chopped up into 4 quartiles. So the box is at the bottom end of the box is at the first quartile, the third quartile. This is called the interquartile range between them, IQR, and that defines where the whiskers are. And so that's how we kind of map the number of kind of flows that we see per sample per hour over all sites over the whole year. But I think what's really interesting here, and this is not something that we fully explored yet, and again, happy to discuss more, is these outliers, right? Because on the bottom part of the graph, it's all fairly well structured, and I think there is some degree of averaging is not the right word, right? Since we're dealing with medians, but there's a baseline that is fairly evident here of activity. But I think what's interesting is where those peaks, right? So that tells us something about the extreme cases of network load on Fabric. There's a lot more data along this line that I could talk about. I just wanted to mention a couple of things before we wrap up. So one thing is, this is a huge kudos to Nishant Shyam-Kumar, who did a benchmarking of our DPDK application to see how it reacts over time, in response to workload. Because as I said, okay, we bypass the kernel on the way in, but we're not bypassing the kernel on the way out to the disk. So the takeaway here is there are kernel parameters that we can set that greatly affect the kind of not the latency that we experience when writing when pages that we wrote to are then being written by Linux to the disk from memory. So one ultimate feature here is the amount of memory that we can use. We have an idea of how to relieve this even with less memory, but it would probably involve hardware that is not currently on Fabric at the moment. We're kind of still finding out more about that, but that's certainly a characteristic of the current prototype, right? But we are able in many cases to get line rate out of this using this offload. I also want to tell you more about limitations, right? So one limitation, as I already mentioned, is that its section is approximately accurate, right? So we see things like this Griffin protocol, which I doubt is what we're actually seeing. This is this graph is like a subset of the encapsulation tree of some of the traffic we saw. I saw that this obscure protocol actually uses the same port as the management software of a well-known large network equipment company whose equipment is being used in Fabric. So I think T-Shark/Wireshark, the sector is confusing the two. Something else, there is this kind of stuttering that happens, right? It seems to believe that there is this deep encapsulation. I'm not sure that is the case. So I kind of, the analysis I showed is conservative. It removes these repetitions to avoid giving the impression that there is very deep encapsulation when there isn't. Another limitation is resource contention, right? So Fabric is running both experiments and Patchwork, which is an experiment, right? But we have ideas of how to relieve this a little bit, but it's certainly something that wanted to flag up, that running Patchwork isn't free. And the other is that currently it does offline analysis, right? We have ideas on how to improve this for online analysis, but that's not something I want to cover in this talk. Okay, so basically, to sum up, contributions are that we did a study of Fabric resources and their utilization. We used this in the design of Patchwork, and I talked about the design, the profile of the profile we got of Fabric up to this point. food for thought includes, what would you like to know from the data, right? So we have a lot of data we can analyze, and we're trying to convey this in a way that's meaningful based on the literature, the related work of providing different types of networks, but always open to the idea of input from the community. Something that would be interesting, but it's not in the scope of the project, is how to link the data plane view of Fabric with the kind of the control, the locator view of the network of Fabric, right? So that we can better correlate more tightly the network activity with experiment activity, right? Currently they're decoupled, but that goes beyond profiling, right? That's something which is more just. So anyway, to wrap up, I have a huge number of people to thank at a variety of institutions, without which we'd have had a much harder time doing this work. They've all helped us tremendously in the various logistical and technical parts of this work. So with that, thank you all. And if you don't happen to ask any questions now, or we're out of time, feel free to reach out at any point. I'm happy to pick up.
All right. Well, thank you so much, Nick, for going through that. We have a little bit of time before the top of the hour. I've unmuted everybody if they want to ask their question. James did type one into the chat, which I'll read out. What do you consider headers when analyzing the header and encapsulation size? I.e., would you consider DNS request and response fields to be headers, or do you stop at the TCP UDP?
Great question. The answer is yes. We are as expansive as possible when it comes to headers. So we actually do see DNS. So we see DNS. We see also control stuff like DHCP. So we see leases going out. DNS does show up over here, and we see ICMP traffic, right? So echoes and replies. So the Spectre and T-Shark very helpfully breaks things down, layer by kind of header by header, and then we take that, we abstract some stuff away, but essentially we keep the structure of what that 200 bytes prefix of the frame contained network-wise.
Okay, thank you. And John Wu has his hand up. Go ahead, John, if you want to unmute and ask.
So, hi Nick. One of the things either I forgot whether you mentioned it or in your paper talks about you want this tool to be useful for individual users, and what you present here are mostly site level or network aggregate statistics. Do you have some examples of how a user might use your tool?
Thank you. Great question. So far, we've only run it internally for user-specific view, or user-specific usage. The reason is that it's only a couple of weeks ago that Fabric made available a permission that users can have to get their kind of to apply mirroring to their specific workloads. So before that, what happens is that you'd have to get a permission that allows you to see everything, right? And understandably, Fabric are very judicious with how they allocate that. But we tried this out internally, and there is no difference as far as what users need to do to run this. So going back to this stages here, the setup would be the same. The observation and collection analysis are exactly the same. What's different is that on the Fabric end, it is more conservative and discriminatory in what it mirrors to the NICs that the users then use to that kind of drive the rest of the pipeline that gather their traffic. But yeah, that's something that we're very keen to have, external people trying it out. So far, we've used it internally, and it's a minor configuration change to run it kind of in a user-specific way rather than globally.
Thanks.
All right. Mark has a question. Mark,
hey
go
Nick,
ahead.
nice work, really interesting. Just to clarify, the encapsulation depth that you're looking at, is that just Ethernet frames that are found inside of Ethernet frames, or does that include like everything that's wrapped up, so like Ethernet plus IP plus UDP?
everything.
Okay,
So
so it's all right. So it's not as high. It's not really as high as it looks, and it doesn't indicate something like um, we're building lots of, or there are lots of tunnels being built inside tunnels that are chewing up network. Then,
yes, exactly
okay,
right.
cool. Thanks.
Great. We're at the top of the hour. If anybody does have any last question, please ask, but I'll thank Nik again. Nik, if you want to send me a copy of these slides, I'll make sure they get posted. And then the talk that we have for the next 2 weeks will be Michael Sinatra from ESNet, and he's going to be going over segment routing. First talk next week will be more of a tutorial for people who don't know how it works or may need a refresher, and then the second talk will be a little bit more advanced the week after. So thank you all for attending today, and hopefully we will see some of you over the next 2 weeks for Michael Sinatra's talks. Thank you all.